For this fifth review slide, let's take a look at conduction through a 1D cylindrical geometry. In this case, we can write Fourier's law, but in this case, the area term becomes 2 pi r L, where L is the length of the cylinder. Now, because the area will vary as a function of r, that means that the heat flux would also be a function of r, because obviously the area term is a function of r. The heat equation, which we'll take a look at, will do for a case of zero internal energy generation and steady state, gives us yields an expression that is again a second order or ordinary differential equation. Now again, we're showing this without actually doing the derivation, but it is available in the textbook. The solution, or the general solution for this second order ordinary differential equation, is given here, and again you have your two unknown constants which then need to be solved by specifying boundary conditions. In this case, we're assuming a cylinder that has an inner radius R1, which we can specify as being at a constant temperature T1, and an outer radius R2, again being held at some specified temperature T2. Once we've done this, we can utilize these boundary conditions with the general solution to obtain this particular solution. And again, I'll point out that here is your variable R. So the temperature will vary through the cylinder as a function of the radius. Now, once we have this particular solution with the temperature field as a function of R, I can take the temperature gradient of it, so taking the derivative with respect to R, and we're going to be able to plug that back into Fourier's law. Doing that, we get this initial form, and we notice that we have R's that will cancel out. And of course, this is something that we would expect because we want a constant heat rate through the cylinders with no variation. We don't want to allow, or physically we're not going to allow for energy to build up and be stored somewhere inside the cylinder because we're assuming a steady state solution. So we can, having taken the R's out here, and now combining terms, we can introduce the thermal resistance for cylindrical geometry, and we're writing the expression here. And again, we have it as a function of known geometry, R1 and R2, the thermal conductivity of the material, and again this length, which may or may not be specified. So again, it's often, as typically shown in your textbook, is that this negative sign will be multiplied through, which flips the order of T1 over T2. So sometimes you want to be careful about that. So if we go, we can take a look at a quick example problem. Now this is again is the typical geometry that we've been looking at. So we have a specified inner radius and outer radius and specified wall temperatures T1 and T2 and a known thermal conductivity. So we're going to utilize this form of the equation and this expression for thermal resistance. So we take our values, and just to point out, when you're, in this case, doing R1 over R2 and taking the natural log, you end up with a negative sign. And in this case, doing the denominator, we don't have a specified length here, so that's going to come out, just we'll keep it as a variable. And the units of the thermal resistance is meter Kelvin per watt. Now, taking the thermal resistance, putting this in the denominator, and making sure we carry our negative sign with us, and now we take T2 minus T1, in this case 16 minus 325, which is again going to yield another negative value, and my negative signs are going to cancel, yielding a positive value for the heat transfer through the cylinder. Since we were not specified a particular length, we're going to report our answer in heat rate per unit length. In this case, the values numerically works out to being 476 kilowatts per meter. And the positive value, the positive heat rate, indicates that heat is moving from R1 to R2. And this is, again, the way we've defined our coordinate system, the way we've defined our direction of the heat vector. So again, if you want to make sure that that makes sense to you in terms of how we're utilizing and handling the minus signs and how we are designating the particular directions. So that finishes up this review of heat transfer through a 1D cylindrical geometry.